This video goes along with section 9.2 in your textbook, and here we're going to talk about sample proportions. First off, we need to review the notation that we're going to use when we're talking about sample proportions. And actually, before that, let's talk about what we mean when we're talking about a proportion. If we've got a proportion, that means that we're going to look at data that the values in your data, I guess I should say, are going to be something between 0 and 1, because it's just going to be a percentage. If you've got data that has a value greater than 1, then that's going to give you a clue that you're not looking at a proportion. You're probably looking at a mean situation instead, which is what we'll talk about in the next video. So then back to notation. We use the letter P to represent a proportion. Remember, this is different than the P that we talked about in Chapter 8 when we were talking about the probability of success. P here stands for proportion. If we just use the letter P, that means the proportion that comes from the population. So it's like the true proportion if we were able to take a census of our population as a whole. If we use the notation P hat, that is the proportion that we're taking from our sample. Now let's think about the definition of P hat. P hat is just a proportion that we get from taking the count of the successes that we have in our sample Sorry, I got interrupted. So here we're defining P hat, which is the count of successes divided by the size of our sample. Now, as we perform or we take more and more samples, the count of successes that we get in each sample, or the number of trials that we run, that's going to vary. So we can represent the count of successes as some random variable x. The size of our samples shouldn't change from trial to trial, so that's going to be a set value n. So using this definition, we can come up with some values for both the mean of P hat and the standard deviation of P hat. For the mean, we can represent that as mu of P hat. So again, this is a theoretical mean that we're calculating here. And what we need to do is, we just said, first of all, that P hat is equal to x over n, where x is a random variable representing the number of, or the count of the number of successes we have for each trial. Now, if we either have a success or a failure for each trial in our sample, that means that we actually can use a binomial distribution for the count of x. Since we have a set number of observations, that's n, we're going to have either success or failure, and each trial will be independent, and finally the probability of success for any one trial or any one observation in our sample will be the same. So that's why we can use a binomial distribution for x. Now, for any binomial distribution, we saw in the last chapter that the mean for that distribution is going to be n times p. So that means that if P hat, sorry, I probably should have written this over here. Let's see, E of x, sorry, is n times p. So that means if P hat is given as x divided by n, then the mean of P hat is the expected value of x divided by n. And we know from our rules about means that if we multiply a mean by a constant, which is the same thing in this case as multiplying by 1 over n, we can pull that constant out. So this is going to be the same thing as 1 over n times the mean of x. And we just said a moment ago that the mean of x is equal to np, so I can plug that in for E of x. And hopefully you notice that the n's conveniently cancel out, which means that the mean of P hat is always just going to be equal to P, where P, in this case, conveniently enough, represents our population proportion. That's also the same thing in the binomial setting as saying what is the probability of success. So the mean of P hat is equal to P. So I just walked you through the derivation of how you go from using the fact that X is a binomial random variable to getting the mean for P hat. I'm not going to go through the derivation for the standard deviation just for the sake of time, but if you want an explanation, you can come see me, or there's a partial explanation in your book. But the formula, which is what you really need to know, is that the standard deviation of P hat is given by the square root of P times 1 minus P divided by N. Again, where P is the population proportion and N is your sample size. Now, we did just base those two definitions for the mean of P hat and the standard deviation of P hat on the assumption that X, the count of successes in our sample, follows a binomial distribution. Now, we do need to be cautious about this. We can only use these formulas when the sample size is only a small portion of our overall population. For example, if your population only has 100 people in it and you decide to take a sample of 75 people, then you're not going to be able to use that equation there because your sample size is almost the same size as your population. So this is going to give us one rule of thumb, we can call it. So we can only use those definitions for the mean of P hat and the standard deviation of P hat when our sample size, or excuse me, when our population size is at least 10 times as large as our sample. I guess I shouldn't even say definition, I'll say formula. Give me just a second, I'll get this typed up. Okay, so here's rule of thumb one, and just to reiterate it, you should only use those formulas for the mean of P hat and the standard deviation of P hat when your population is at least 10 times as large as your sample, and you can represent that statement as capital N, that's your population size, needs to be greater than or equal to 10 times lowercase n, which is your sample size. So that's one rule of thumb to keep in mind. There's also a second rule of thumb that you should be aware of, and this is related to back to something that we talked about in Chapter 8 when we were covering binomial distributions. Back in Chapter 8, we said that we could use a normal approximation to estimate a binomial distribution under certain circumstances. And the same criteria apply in this case because, again, remember that we are using that binomial distribution to help us estimate what P hat would be. So again, this is exactly the same rules we saw in Chapter 8. We can only use that normal approximation to apply to the sampling distribution for P hat when n times P is greater than or equal to 10. Again, n is our number of samples, P is our population proportion. So n times P has to be greater than or equal to 10, and n times 1 minus P has to be greater than or equal to 10. There are some good examples in your textbook beginning on page 586 that walk you through these ideas. So I strongly recommend that you take a look at those examples and read through them carefully.